So, we continuing with our discussion on the concept of false paths and how you can identify and characterize false paths in a circuit netlist. Just to recall, false paths are important to eliminate certain paths from timing analysis, to identify the criticality of paths and so on and so forth, which can help in avoiding unnecessary calculations and unnecessary processing when you are trying to optimize a circuit with respect to the timing characteristics and parameters. So, here we talk about something called static sensitization. So, we shall be explaining this concept with the help of an example. So, what I say is that given a circuit, some path is said to be statically sensitizable if there is an input vector such that, so from the input to the output any changes can be propagated, means all the other inputs to the gates that lie along the way are set to non-controlling values, and this static sensitization will be independent of gate delays. Let me illustrate this with the help of this example. Let me work this out. So, this example whatever is given is a circuit like this. So, let us give some names to the gates. G2, this is the circuit which is given, this combination circuit. Just if you make a quick computation, what is the logic function that is realized by this circuit? A B, this is a NOR gate. So, the output will be A bar B bar. This is an AND gate, this output will be A B. OR gate, this will be A B OR C, and this is AND gate, this and this. So, A bar B bar and A B will cancel out, A bar B bar C. This is the final output, right. Now, what we are trying to say here is that, let us consider these paths. We consider two paths. First path is starting from input A to gate G2 to gate G3 to gate G4 to the final output, and also similarly from the input B. So, we are saying that these paths are not sensitizable. So, what do you mean by sensitizable? You recall we mentioned that if I have a sequence of gates along a path, let us say I have an AND gate, then I have an OR gate, let us say I have another NAND gate along a path, the other inputs are there. So, if I want to propagate a signal from one line, let us say from here, so along this path, so I have to apply non-controlling value to the other inputs along the gates, like this transition will come to the output of this AND gate if I apply a 1 at this input. For an OR gate I have to apply a 0, for a NAND gate again I have to apply a 1. This will ensure that these transitions will propagate, and depending on the gate, the other inputs or the side inputs must be applied non-controlling values, so that the change can propagate, right. So, in this circuit also let us try in the same way, that can we propagate a signal from A via G2, G3, G4? Let us try. From A via G2 means I am trying to talk about this path, A via G2. So, this is an AND gate. So, I have to apply a non-controlling value 1 in the other input, then via G3 is an OR gate, I have to apply a 0 in the other input. So, again I get into G4 AND gate, I have to apply 1 here, then only this will propagate to the output. But the trouble here is that if you just look that as soon as we had applied a 1 in this other side input, this B also has become 1, right. This means that I have to apply a 1 in B. Now, this is a NOR gate, a 1 in any of the inputs will make the output 0, but we require a 1 here, there is a conflict. Same thing you can check from the other paths. Just by applying non-controlling values in the side inputs, we cannot sensitize these paths. This is actually true, just to tell you, for these circuits whenever you have a something called reconvergent paths with unequal inversion parity. Like see, there are fan outs. From A there is a fan out connection, one is going via G1 then to G4, other is going via G2, G3, G4. Now, in one path there is one inversion and NOR, other path there are no inverting gates. So, in one path the number of inversion is odd, other path is even, they are again merging into a gate. This is called reconvergent path with unequal inversion parity. So, whenever such a thing is there, there is a likelihood that you will not be able to sensitize these individual paths. So, this is a drawback. Now here why we are talking about this? You see, here your static timing analyzer, what it will tell you that well, this path can never be sensitized, this will be identified as a false path, and it will say that well, this is my only path which is of interest. So, my longest delay is true. Longest delay is 2, right. But now, let us suppose, now what I do is that this same circuit, I am just applying some inputs and I am trying to do a timing simulation and see what is happening. So, both the inputs, the third input is at 0, the first two inputs are going from 1 to 0 at time t equal to 0. So, let me show you the timing diagram, so it will be good for you. So, I am just marking the time. So, this is t equal to 0, t equal to 1, 2, 3, 4 and so on. So, now to show the inputs, this A makes a 1 to 0 transition at time t equal to 0. So, let us say that the A input is like this, B is the same, B is also making a 1 to 0 transition at time t equal to 0. C is always 0, let us say C is constant 0. Now, let us just assume that the gate delays are all 1. So, let us say 1 by 1, what will be the output of G1? G1 is the NOR of A and B, initially both are 1 1. So, it will be 0 and after that both are 0 0, it will become 1, but delay of 1. So, it will become 1 after 1 unit delay here and it will remain 1. Talk about G2. G2 is AND, both of them will be 1 and once they are 0 they will become 0. So, again with a delay of 1, G2 will remain 1, it will become 0 here. G3, G3 is the OR of G2 and C. C is always 0, so it will be G2 itself, but with a delay of 1. So, it will with a delay of 1, it will become like this. And finally, G4, what will happen? G4 is the end of G1 and G3, G1 and G3. So, you see it will be 1 during this region, but with a delay of 1. So, it will be so both are getting 1 here. So, after delay of 1 this will come here. So, it will come here, it will remain till here. So, you see here. So, our false path detection algorithm tells us that this is a false path, therefore, this is a true critical path, the longest delay is 2. But for a particular input, what we have found is that the output is getting stable only after time t equal to 3, right. You see there is a glitch in the output, temporary change, because output is supposed to be 0, a bar, b bar, c. I am applying say a 0, b 0, c 0. So, the output should be 0, but in between it is going to 1 periodically, then it is stabilizing to 0. So, the output is getting stabilized only after delay of 3 and not 2, right. This is what this calculation says, right. So, here what we are saying is that the static sensitization method that we are following, this is doing some delay underestimation. So, the true delay is 3, but it will give us a delay of 2, which is an incorrect condition, right. So, what is wrong? So, the wrong, I said one thing I had said that there is a reconvergent fan out with unequal inversion parity, that condition is holding, that is one problem. But with respect to the controlling and non-controlling values, the issue is that we are ignoring the timing when the values are becoming controlling and non-controlling, because you see the values of the side inputs are not constants, they are also changing in time. So, sometimes they are controlling, sometimes they are non-controlling. So, it is not that statically in a constant way you are applying a fixed value. So, temporarily they might, the status might change, and that creates the problem, right. So, this is what is mentioned here. The same signal can have a controlling value at one time and non-controlling value at another time. So, let us try out something called timing simulation. Let us see whether this gives us the correct result. Timing simulation means we simply calculate the times and see when signal transitions are taking place. So, we again take an example like this. Let us assume that these are some gates, some buffers, and gate, some hypothetical delays, let us say 2, 1, 4, 1, 1. So, let us assume that there are 2 inputs, the transitions are taking place at time t equal to 0. Look at the delays of these gates. This transition will go to the output with a delay of 2. So, this transition will be taking place at 2, delay of 1, 1, delay of 4 at 4. Now, this gate is providing a delay of 1, but here you see at time 1 it is going high, at time 2 it is going low. So, between 1 and 2 both are high, therefore, there will be a delay of 1 again. So, between 2 and 3 there will be a period where both are high. Look at the output of 1, this signal is going 1 at 4, but by 4 it is already at 0. So, the output is steady 0. So, timing simulation will show that if you apply this, that means one input is 0, other input is also 1. So, this is basically an AND function. So, the output is supposed to be 0 and it is already 0. So, it should be good, that means delay is 0. But you see for this case the delay is showing to be 0, but suppose I reduce the delay of one of the gates, let us say this was 4, let us make it 2, and here let us do the same calculation again. This part is same. So, here this transition will be appearing earlier at time 2. So, here also it is making a transition. So, now if you do an AND, these 1s and 1s will overlap. So, there will be a transition after a delay of 1 between 3 and 4. So, you see only after time 4 the output is getting stabilized. So, for this case, as soon as we reduce the delay for the same input values, same input transition, the delay is be showing at 4. So, this also gives you a very interesting thing. Sometimes a static timing analyzer might show you an increase in delay whenever you are reducing the delay of some component. So, you expect things to become faster, but as this example shows that for the same set of input transitions, earlier there was no delay virtually because the output is 0, it is always 0, but now only after time 4 the output is getting stabilized, right. This is one issue. Fine. So, what is wrong here? This is one thing I just now mentioned. If we reduce some gate delays, it is possible for some delay estimate to increase, but this is actually contradictory, right. So, we would expect that if I reduce a gate delay, my path delay or circuit delay should also reduce, but here it is happening the other way around. So, my timing simulation is not proper in the sense that even if I am reducing the delay of a gate, my timing simulation is saying that the delay is increasing. Okay. So, this is not acceptable because in practice many gate delays can actually get reduced, because the gate delay values that we usually use in the simulation, they are upper bound. We say a delay is 4, which means this is not actually 4, the maximum delay is 4, because when you are fabricating gates in a chip, there can be lot of variations in fabrication. Some gate may be 3, some gate may be 2.5, some gate may be 3.8. 4 is the maximum limit you are saying, that is the worst case delay, right. So, here actually we are implicitly analyzing some circuits where gate delays are within some upper bound. Okay. So, this creates a problem. Now, we need some simulation where some property called monotone speed up should be satisfied. So, what is monotone speed up property? This says that if you are given a circuit C, then we can get an circuit C dash by reducing some gate delays, and in the process the delay estimate should also be reduced or at least be equal, not go up. There is a monotonicity. So, if you reduce some of the gate delays, your total delay estimate of the circuit should not increase. This is the condition which is mentioned. There has to be a monotonicity in the property. If this property is satisfied, you can say that your algorithm satisfies the monotonicity property. Now, timing simulation, as we have seen, obviously does not satisfy this property, but we can make some modification and see just one simple thing. I am explaining with an example. This is something which is called X value simulation. This is also timing simulation, but we are not showing exact signal transitions from 1 to 0 or 0 to 1. We are using some special logic value called X. This notation where the transition is taking place at time 4, this means that this rising edge can occur anywhere between t equal to minus infinity and 4. That means this change can occur anywhere in the past history. So, if you follow this X value simulation, it can be shown that the problem that you are facing, that you will not be facing anymore. Why? Let us say you are applying 0 here, you are applying say 1 here, and you are saying that previously it was x, that means this condition was true. This transition can happen anywhere in the past, not exactly at 0. So, after delay 2, this 0 will be shifted to 2, this 0 will be shifted to 1, this 0 will be shifted to 4, this has a delay of 1. So, this if you just look at the property of this x, this will shift to 3, because at 3 definitely both of them are at 0 after delay 1. Before you do not know, both may be at 1, that is why it is x. And finally here 4 you are going up, 3 you are going down. So, at 4 definitely you are going down. Okay. So, here you can easily see the simulation will tell you that only after 4 it is getting stabilized, unlike the earlier case where you are saying that in the output you are getting a constant 0. So, if you are using x value simulation, you can get some accuracy in this calculation, right. So, this is referred to as timed 3 valued simulation, where instead of 0 and 1 you have an additional state called x, whose interpretation we have already seen here. It means that the signal transition can take place anywhere before this time, not exactly at this time, right. So, with this modification the monotone speed up property is satisfied. This is the good thing. Okay. So, now we look at another approach to detecting or identifying false path, that is based on using a SAT solver. SAT stands for satisfiability. Satisfiability problem is a very well known problem in switching circuits, where given a Boolean function in some special form, say for example the product of some forms, the SAT solver will try to find out whether there exists some combination of the input variables for which your given function is equal to 1. If so, it will also tell you for what combination of the inputs the function is 1. That is the task of the SAT solver. So, SAT based fault path analysis, what it tries to do is that, now the thing is that SAT solver is a very general kind of a tool. It can be used to solve a wide range of problems, okay. And the SAT solvers that are available today, many of them are freely available. They run very fast and they can handle quite large number of variables, thousands of variables they can handle, okay. Now, this is what I mentioned, that a Boolean function is given in product of some form, and a SAT solver will try to find out some values of the variables for which f equal to 1. So, let us see how the false path analysis problem can be mapped into a product of some expression, and you can use a SAT solver to solve it, right. So, the SAT formulation goes like this. This is the most important step whenever you are using SAT to solve a problem. You have to map it properly. The decision problem is here. We are trying to ask this question: is there any input vector for which the output gets stable only after t equal to capital T? Like here it is something like this. Suppose we expect that capital T is our time budget within which everything should get stable. Now, we are asking the SAT solver, can there be some input combinations for which the delay can exceed capital T? This is the way we are posing the problem, right. So, this is one possible formulation. There can be other formulations also you can try out. So, here what we are doing, we are trying to characterize the set of all input vectors S capital T that make the output stable, means earlier or at t equal to t, no later than. So, ST is a notation, which means this denotes all vectors for which the signal becomes stable within time t, and capital S denotes all possible input vectors for which the output becomes true or something. Now, the SAT problem, the question you ask is that whether the set difference S minus S capital T, is it empty? See, this should be equal. So, for all possible test vectors, so you should have this property, the output should be stable within ST. So, if you do a set difference S minus ST, this set should be empty. So, take a set difference and check for emptiness, but if you say this is not empty, this means this is not satisfiable. That means there is a problem here, there is a timing violation. So, suppose corresponding to S and ST, the corresponding Boolean functions are referred to as F and FT. So, the expression that you are giving to the SAT solver is F and not FT. Is this product satisfiable? Because set difference means this is true and this is false, this is true and this is false. Okay, let us illustrate with an example. So, a very simple example here. So, we consider this circuit. So, let us just work out this circuit once more. So, we have a circuit like this. So, essentially we have like this, A and B are applied to both these inputs, and you have an OR gate, C is applied here, then you have an AND gate, this is applied here. So, this is G, these are the delays of the gates, all assumed to be 1, let us call it D, let us call it E, let us call it F. So, if you just calculate the output expression, your D is A bar B bar, this already I have just mentioned earlier, E is A B, F equal to A B or C, and therefore, G becomes AND of D and E, D and F. So, it becomes A bar B bar C, this is what G is. Okay. Now, in this problem, in this example, so here we assume that all the primary inputs are arriving at time t equal to 0. So, here we assume that all primary inputs are arriving at t equal to 0, all gate delays are 1. So, the question you are asking is the output stable at time t greater than 2, because 2 is our expected deadline. So, here our timing analyzer told us that the delay should be 2. So, let us see whether 2 is the correct figure or not. So, we are just showing you with this example that how the SAT formulation is actually done. So, how you do we map this into a Boolean expression. So, we use a notation like this G1 comma t equal to 2. This denotes the set of input vectors under which the output G gets stable to a value 1 no later than time t equal to 2. You see G1 t equal to 2. So, the output is supposed to be 1. So, when it will be 1? When this is an AND gate, both D and F should be 1, when just one time unit before the delay of this is 1. So, this will be equal to D 1 comma t equal to 1 and that means intersection F 1 t equal to 1, because time is 1 less. So, if D equal to 1 means what? Both the inputs of this NOR gate should be 0 and 0. So, it is A 0 delay is again 1, now time will be 0 and B equal to 0 both together, and F equal to 1 means is an OR gate. So, either E will be 1 or C will be 1. So, C will be 1 or E will be 1. So, if you just now calculate A 0 T 0 means what? That means at time t equal to 0 when all the inputs are coming, you are saying that A is 0, I write it as not A. At time t equal to 0, B equal to 0, I write it as not B, and here at time in t equal to 0, C equal to 1, that is only C. Intersection at time t equal to 0, E equal to 1, you cannot say E at time t equal to 0, it is undefined. So, this is empty phi. So, this is only C, A bar, B bar, C. So, let us call it S1 t equal to 2. Well, here and if we just assume t equal to infinity, that means the correct logic function, this already we have seen that the function that is realized is A bar B bar C. Okay. So, this is defined as the onset for t equal to infinity. Okay. So, delay is not considered. So, we see that these two are equal. Okay. So, if you subtract these two, it becomes null. So, for the onset there is no problem, but let us look at the offset z 0 t equal to 2. So, when g equal to 0 means any one of d and f can be 0. So, d equal to 0 at t equal to 1 or f equal to 0. If f equal to 0 means both e and c are 0, f 0 means both c and e are 0, and d 0 means any one of them can be 1, a is 1 or b is 1. So, a is 1, you now write down, this means at time t equal to a equal to 1, that means a, odd means plus, odd notation, this is b, c 0 t 0 is c bar, intersection phi, this becomes 0, only a plus b. But offset, this z 0 t equal to infinity already have calculated, should be a plus b plus not c. So, if you take a set subtraction, these are not the same. Okay. So, to summarize, you have got this as a plus b, you have got this d. If you take a set difference, that means I said this not this, then you get a bar, b bar, c bar. That means there is one input combination 0 0 0 for which delay equal to 2 is not satisfiable, the delay will be equal to 3. Okay. So, this is roughly the idea how this method works. Okay. So, to summarize, false path aware analysis is important, and this is quite well and understood. Many practical algorithms exist. So, we just mentioned a couple of them. They can handle very large circuits quite easily because their computational complexity is not so high. So, the problems that need to be looked at is that incremental analysis, if you make small changes in the circuit, do we have to do the analysis all over, or we can do some kind of incremental analysis? And this logic optimization also, we usually do a lot of optimization. So, when you do optimization, can you integrate the same process within that? And again, for deep submicron issues, we need to consider the crosstalk and noise issues. Some of this we shall be discussing later. Okay. So, with this we come to the end of this lecture. Thank you.